Chelsea Dad here today. She's recently moved to become the program director of Curious Minds. But she has been involved in IODP in her previous life. And she's going to talk today about the paleoceanography of the Bering Sea and implications for past climate reconstructions.
Okay, thanks, Stefan. Hopefully I'll be involved with IODP in my future life as well. Hopefully still keep that going. So I'm going to talk a little bit about the Bering Sea and some of the work that we did on IODP Expedition 323. Okay, now just keep.
Sorry, I'll
No, it's okay. I can just, I'm standing right next to it, so I can take it. So Expedition 323 was in July to September 2009, so a little while ago now. And we sailed from Victoria in Canada into the Bering Sea and then down to Yokohama at the end of the expedition. The strange things. This was a paleo oceanography expedition. Just a few statistics about this. We drilled at 7 sites, so these are the red dots that are on here. We had initially intended to drill at a few other sites, and you can see some of the grey dots in here. They fall in Russian waters, and we never got permission from the Russians to drill at those particular sites. And what was interesting is at the same time that we were there, the Sonography was out in the Bering Sea drilling at all of our sites, and they got permission from the Russians to drill at those sites that we couldn't. But of course the Sonography can only take shallow cores, so we were able to drill quite deep. We took a lot of cores. We covered a lot of sediment, so 5 kilometres, nearly 6 kilometres of sediment. Took a lot of samples on the ship, but then post-cruise we took another 60,000 samples, so it was a very intensive sampling expedition. And we recovered sediment back to about 5 million years, depending on which age model you use. So if we just have a look at this picture here, you can see the Bering Sea. There's several different parts to the Bering Sea. We've got a large continental shelf, so fairly shallow water area that's shown in white there, and then a deep water basin adjacent to that. It sits behind the Aleutian Arc, so we've got the Aleutian Arc going up into Alaska. We've got Siberia over here and Kamchatka. So there's a number of different areas that we looked at. These sites here are on the continental slope, very much influenced by sediment coming from Alaska. There are 2 main rivers that come from Alaska and 1 main river that comes down from Siberia, delivering sediment to the continental shelf. And then the deep water areas that are much less influenced by that continental sediment. You'll see that there's a ridge that goes through here, and I'll talk about that a little bit. This is known as Bowers Ridge that we drilled on, and there's a continuation up into what's called the Shershoff Ridge up here. That's fully submerged, and no one had ever drilled into the basement of this ridge before, and we managed to get that basement to prove what the ridge was made of during the expedition. So why did we go to the Bering Sea? It's a marginal sea, as I said, so here we can see the Aleutian Arc, so it's a marginal sea that sits behind that Aleutian Arc. It's very different to many of the marginal seas, particularly those that we're probably familiar with in the Western Pacific. One of the main differences is the arc runs the opposite way. It's at 90 degrees to most of the arcs that we see in the Western Pacific, and that has implications, of course, for mantle flow in the area. And you'll see that there's really no spreading system in that marginal sea. So unlike the Western Pacific back arc basins, they've all got small spreading systems in them, and this one doesn't. So there's no spreading system in this basin. The area here I've shown some of the different currents you can see, so some of them flow along the Aleutians, and there are a number of passes in the Aleutians where water travels through. This area has extremely high productivity. It's known as the green belt. And so we were able to sample sediments that had really abundant microfossils to use as paleo proxies. It's also important because of the gateway up here. So the Bering Sea Gateway is open at high sea level times and is closed when sea level is low. And that's a really important gateway because it allows mixing from the Pacific, so water is coming in from the Pacific into the Bering, travels up into the Arctic Ocean and then out into the Atlantic Ocean. So it allows mixing of all those different oceans. So when this is closed, that ability to mix the waters is cut off. And we know that North Pacific intermediate water is formed in the Bering Sea, and there's a large amount of sea ice that forms in that basin. And here you can just see some of the sediments, and I'll talk about the sediments in a minute. But these are all diatom frustals, so very, very packed with diatoms. This shows the aleutians and the flow of water in and out of the aleutians. So you can see we've got flow into the Bering Sea and flow out of the Bering Sea. So as the water from the Pacific comes along the Aleutians, it passes through these straits and a large part through the very deep Kamchatka Strait, and water comes out of those passes as well. Just up here you'll see the Bering Strait, and you can see that water is only flowing out of the Bering Strait, and you also see from that diagram just how shallow that Bering Strait area is. So it's sitting on the continental shelf, and you can see that's 500 metres, so very, very shallow, so easily blocked when the sea level falls. We divided the sites into the two areas, those that are on the slope, so we have 4 sites on the slope and sites on the Bowers Ridge. Bowers Ridge a long way from the continental masses, so very low sedimentation rates, up to about 12 centimetres per 1,000 years. And so that we were able to drill down to 5 million years in 600 metres. Very high sedimentation rates in contrast on these slope sites, with sedimentation rates up to 58 centimetres per 1,000 years. And so drilling down 745 metres, we only got to 2.1 millions. Looking at the sediment is mainly made up of diatoms. So here we can see that the sediment, this is just one of the diagrams we used on the ship to classify the sediment we were looking at, and we saw contrast between diatom ooze and diatom silt were the main things we saw. Some of the areas got diatom-rich silt, and we did get some ashy material being very close to the Aleutians and to Alaska, which are both volcanically active. There's that slide again with all the diatoms, so mainly diatom frustals in the sediment, but there were some other organisms, radiolaria, silica flagellates, and foraminifera, and some calcareous nanofossils, but not very many. So we had calcareous nanofossil person on the ship, and for a large part of the time she had nothing to do. We just didn't find them. The siliciclastic component that we looked at was mainly mud, and we did find some sand, particularly on the slope sites, and I'll show you some of that in a minute, and a lot of ice rafted debris. So there were very small pieces of ice rafted debris, right up to really quite large pieces. So we're looking at a cobble-sized piece here, and that actually blocked the drilling in that particular spot for a while. And I looked at those as one of my research projects after this expedition, and I'll show a little bit of that data. As I said, there were quite a lot of ashy material in the sediments as well, particularly at site U1339, sitting here right adjacent to the Aleutians and Alaska. So lots and lots of layers of volcanic material in there. The ashes varied from felsic ashes, so some quite light coloured ones, to these very dark coloured ashes, and of course that reflects whether they're high silica or low silica ashes. Most of them are the typical of deep sea ash layers, quite sharp bases and much more bioturbated tops, little graded beds. And I also looked at the ash, volcanic ash, as a project after this. exhibition. Looking at the ash layers, the distribution of ash layers is quite interesting. There's a sort of a peak in the ash distribution in this area from about 1.5 to 2.6. And it's interesting that at about the onset of North American glaciation is where the ash starts to pick up. Now, whether there's a correlation between more volcanism at that time or not, I don't know. But we also see the same thing found in the North Pacific. This shows magnetic susceptibility at ODP site 882, which is just on the other side of the Aleutians. And each of the peaks in the magnetic susceptibility here is most likely an ash layer. And you can see that once again there's this peak in volcanism that relates to about the same time that we see in all of that area. Most of the ash appears to come from Alaska, with some coming from the Aleutians. Okay, so I'm going to divide it into the two different areas and have a look at these sites. So this is the Bowers Ridge sites. This is a detail of that area, so you can see we were drilling on the high points in the Bowers Ridge, 1340, 41 and 42. So just looking at the sedimentation in those sites, varied a little bit. In 42 we got four different units, but we missed unit 2 at this particular site. You can see here that the uppermost unit that we looked at was a Diatom Silt, so a large amount of diatoms, but also some silty material. Unit 2 is a diatom ooze. There's a change at about 2 million years from one to the other. At this site here, we also got a sandy unit. A little bit difficult to interpret. The drilling with the piston coring doesn't drill through sandy material very well, so we've got a lot of what they call flow-in, where the material just gets sucked into the drill core and you lose a lot of the layering in there, so a little bit difficult to interpret. But that was quite a different unit. And then this is the volcanic basement, and we drilled into the volcanic basement. As I said, it had never been drilled before. So we do now know that the Bowers Ridge is a volcanic feature, probably an ancient arc. Looking at each of those, the first unit is the Diatom Silt. This is what it looks like in drill core. You can see that it's laminated, though they're fairly faint in this area. So the fact that we've got laminations in the sediment tells us that it was probably not that well oxygenated, so there weren't a lot of things living in the sediment to bioturbate the sediment there. When we looked at individual laminations, it was quite interesting that some of them were made almost entirely of one species of organism. So this one, the diatoms here, plants, just this one species, this very elongate pinnate diatom, makes up these little white layers. And when we looked at one of these dark layers here in the laminated sediment, it was nearly all silicoflagellates. So there was something happening at the time that led to a sort of bloom of these different organisms or plants that then were deposited in the sediment. We did find a number of really well laminated intervals, and we could correlate those with the number of interglacial cycles, and I'll show a little bit of that as I go through. We could see it here at the Bowers Ridge sites, but much better preserved at some of the slope sites. And the idea is that the laminated ooze represents the interglacial times. So the other units, as we go down in the stratigraphy, unit 2 is the diatom ooze, and again you can see centric and pinnate diatoms making up most of the sediment there. There were fewer laminated sections than in the uppermost part of the sequence. Unit 3, we're not sure what the age is, but it could be considerably older, and it was characterised by lots and lots of these very large sponge spicules and much sandier. Just to contrast those Bowers Ridge sites, they are the sites here with basement. You can see the Diatom Silt at the top, the Diatom ooze as you go down with the boundary around about 2 2 million years. These are the sites on the slope, and you can see from the colour change that we're getting into silts and clays and silty clays with far less of the diatom material. But you can see there's still a diatom silt component represented at these sites. So we're seeing a lot more siliciclastic component coming off the shelf from the land, mainly from Alaska there. Hole 1339 is quite different. It's got a lot of diatom ooze in there and also a very, very high ashy component. This figure just highlights the difference in the sedimentation rate as well. So this is Unit 1, just at the top of the Bowers Ridge sites, and here it is much expanded out on the slope sites. This picture here shows some of these laminated intervals. So we got these very nicely laminated intervals shown in green here, all the way down through the core. It was quite nice to see that the contrast between the laminated intervals, which were beautifully laminated, and then it would just go straight into intensely bioturbated sediment. So the amount of oxygen on the sea floor over time was varying very rapidly from very well oxygenated conditions to areas with very low oxygen. What I'm going to do now is just have a look at some of the different sites. So this is one U1339. As I said, it has abundant volcanoclastic layers, and you can see the ash all through here. These are the IRD, the drop stones that we picked up. So it's strongly influenced by ice sheet variability because it's very close to the continent there, the edge of the continent out on the continental shelf. So it does get the sea ice through there. And you can see the variations between diatom silt, the browny colours, and the diatom ooze all the way through here. And that's showing the glacial and interglacial cycles, so we could pick those up quite nicely and the variation between them. The slope sites you can see here, and this is some of this beautifully laminated material that we were getting at the slope sites. So mostly diatom-rich and diatom-bearing siliciclastic sediments, so quite sort of muddy things. The laminations, again, individual laminations had often just one particular type of microfossil in them. Some of them were foraminifera-rich. We found a lot of sponge spicules, some of them in these very strange little clumps, so this is all sponge spicules in here, suggesting maybe that they were agglutinated forams, that we now can't see the foram and just what remains of its test there. We also found some of these bivalve shells in here. You can see these lovely laminations indicating the low oxygen conditions. And this is some of the laminations in detail, so that we looked at each of these in smear slides, and you can see that they vary in the amount of diatoms and the amount of muddy siliciclastic material depending on the colour in here. So sometimes the laminations were different microfossils, and in this case they were different amounts of muddy material, so it varied on what was producing the laminations. Okay, so we also found some sandy material in these slope sites. So during low stands, we think it was during low stands, there was a lot more sediment being shed from the continental mass, particularly, as I said, a couple of large river systems coming in, delivering these sandy sediments out into the continental slope. We were actually able to correlate some of these sandy layers between the different drill holes that we looked at. Sometimes the sandy layers were very intensely bioturbated, so we would just get the big legs of them. Right in the upper part of the sequence, so here we're looking at the upper 130 metres at one of the shelf sites. We've got a number of these laminated layers, and we were able to correlate. This is at the same site, just in two different holes at the same site, but we were able to correlate them with known climatic events. and one of the sedimentologists that was on the expedition had been working on piston cores from similar regions and was able to recognise these laminated layers from other work that she'd been doing on piston cores. So we could see quite clearly these different smaller climatic events that are changing the oxygen minimum zone in the basin to have laminated and non-laminated sediments at different times. Here we can see the glacial interglacial cycles within the change from diatom ooze to diatom silt. So we're looking at GRA, which is the gamma ray, and this is telling us whether we've got more diatoms or more silt, and we can see that those two alternate in opposite sort of directions, so that as the diatoms increase, the amount of silt decreases, and we get this oscillation between the two. And this is just the siliciclastic component in here. So you can see that there's this change oscillating between diatom ooze and diatom silt. And we think that that is the glacial interglacial cycles being represented in the sediment. I had a look at the ice rafted debris to see whether I could work out where some of this material was coming from, and also to see whether it would correlate with any of the glacial interglacial cycles. So I did a number of things. I, of course, counted all the number of clasts that were there, and you can see there were a lot of clasts at the site right near the continental area along that plateau. Very few clasts made it out to the Bowers Ridge sites, and they were abundant again on the slope sites. For each of the clasts, we looked at the size, but also looked at shape parameters to see whether there was a difference in the number of elongate clasts, equant clasts, plated clasts, and so on. A lot of the clasts that we did see in the core, it was interesting that a lot of them were really well rounded. So you'd expect from glacial transport that you'd have a lot of angular clasts from material falling onto ice sheets being transported out and then having icebergs carving and so on to produce the ice rafted debris. But a lot of this material is really well rounded, and that is typical of ice rafted debris in the Bering Sea from other areas as well. So what I've looked at here is the OP index, and that is comparing the elongate to platy particles. So these are more platy and these are more elongate. So the more elongate ones are more likely to be fluvial, and they become more platy if they've been sitting on a beach. And that's because beach erosion tends to push the clasts backwards and forwards, and it sort of weathers them so that they get a flat shape to them. So we can see that some of the clasts were derived probably by rivers coming in, and others were sitting on the beach for a while. So if you had clasts that were sitting on the beach, maybe that tells you there wasn't sea ice there at the time. But it was all quite complicated because there are a number of factors that would come in here. But it appeared when you look at some of the other clasts, there were a lot of discoid shapes from the slope sites and fewer discoid ones, so beach-like ones, on the Bering Sea sites. But it does look like a lot of this material was delivered to the coast, either by rivers or it sat on the beach for a while, and it was probably being picked up by sea ice and delivered to the ocean by the movement of sea ice rather than glaciers and icebergs. So it's not really telling us whether we have a huge ice sheet present. It could simply be seasonal sea ice. So it complicates the picture. For the youngest 1 million years, where we have our marine isotope stages fairly well defined, I had a look at whether there was any correlation between the number of pebbles or IRD and the marine isotope stages, and I couldn't see any correlation at all. And I think that's because it's related to sea ice rather than just the glacial periods. Now I've put together some of the microfossil work that's been done by others, just to show you what some of the results were of the expedition. So this is looking at the radial area, and you can see, you can't see the names of the radial area very easily, but don't worry about that. We're looking from 0 down to 4.2 million years. But what you can see is there's quite a change coming through here at the time of the Northern Hemisphere glaciation, where we've got some species disappearing and others becoming more abundant. So these ones here are subarctic or transitional species, and they are more abundant lower down in the stratigraphy. And then as we think the climate was cooling with the intensification of the Northern Hemisphere glaciation, we start to get some of these subarctic species coming in. And there's a couple of points where there are changes. But it clearly shows that it's going from more transitional temperatures to more subarctic temperatures in those radial area. So that's out one of the Bowers Ridge sites. A particular radial area that is abundant. So this particular radial area has a low abundance when there's sea ice cover. And what we see from this is this one here, there are periods here when it has quite a high abundance. So that's telling us there were periods when there wasn't very much sea ice. So we can see here that there was less sea ice in the older periods, and then as the climate was cooling, we got more periods of sea ice where the abundance of this particular radial area is lower. And this, one here, this particular radial area species, it is abundant here in the warmer climates, and then as it gets colder, it completely disappears from the record. So the radial area quite clearly show a change from slightly, not warm, but slightly warmer conditions, and then with the Northern Hemisphere glaciation, we change to cooler species. And the other one is from the same radial area data here. We can see this particular species here has very large amplitude changes in the last 2 million years, or particularly in the last 1 million years, and that is thought to be related to the ventilation of the intermediate waters during the glacial interglacial cycles. So we're starting to see an oscillation with those different cycles as you get up to the top of the pole. With the diatom assemblages, again, we can see that there's a change as you go through the stratigraphy. Here we're just looking from 0 down to 2 million years and a little bit older. But we can see there are some species here, the temperate water species, that are abundant, low in the stratigraphy. And the sea ice related species become much more abundant as you go up to the upper part of the stratigraphy, again related to the Northern Hemisphere glaciation that changed about 2 million years. The benthic foram delta 18 so the person that did this work was looking at these benthic forams and trying to see whether you could see the different oscillations related to the marine isotope stages. So here we're looking from 0 to 2.5 million years. One thing that he noticed in putting this together, he was able to get a very nice correlation of his benthic forams with the known marine isotope stages, but he noticed that there wasn't a very good correlation between this information and the information that you could get from the sediment record. So things like the amount of clay there, the amount of ice raft debris, and the bulk sediment contributions. And he suggested that there was such abundance of material that was coming from the land during the low stands that it just sort of swamps what's the signal that's there, and we're not seeing any correlation between these two different records. So it's being masked. But he was able to pick up some interesting things. So his sea ice expanded during the mid-Pleistocene transition. So now we're looking at just from 0 to 1 here with the mid-Pleistocene transition. And he could see a change with his isotope record from the 100,000 year oscillations the more recent, going back in time, going to the 41,000 oscillations. So his data was mimicking the stacks for the marine isotope stages that had been done before. So that was one. Okay, so just in summary, the Bering Sea sites, we could divide them into the slope and the Bowers Ridge sites. The slope one's been very much influenced by the sediment that was coming down from the land, and the Bowers Ridge sites much further. Sediment changes from very diatom rich ooze to diatom silt in approximately 2 million years at the Bowers Ridge site, so quite away from the land. The ice rafted debris is more abundant after about 1.8 million years, but there's no correlation with the marine isotope stages after about 1, and that fits in quite nicely with the FRAM work, that it doesn't correlate nicely with the sediment information. The ash layers are more abundant in the area after 2.5 million years. There's a change from subarctic transitional radial area species to subarctic ones at about 3.6 and then again about 2.7. The radial area show large amplitude variations in the last 1 million years that could be related to the glacial and interglacial cycles. We get an increase in the sea ice diatom species at about 2 million years. And obviously that last one. So that we can see that there is quite a big change in many of the paleo proxies, as well as the sediment types, indicating cooler climates from with a boundary around 2 million years. We can see the glacial interglacial cycles of the last million years in some of the proxies, but not in every. And that's it. I'll just throw up an ad there for one of your own, really. So Craig O'Neill's going to be talking at the next Geological Society New South Wales meeting. Questions?
That was a great talk. Thanks, Kelsey. It was very exciting with the Bowers Ridge that was volcanic. Did you get any ages on those volcanics?
Yes, I didn't, but someone has done that work and it was published just recently. I'm not going to be able to tell you what it was. But yeah, it's easily accessible. So they've got an argon date on some of the volcanics.
Oh, cool.
So you'll be able to add that one to your models.
Yeah.
That's a great talk, thank you very much. I was wondering about this change in volcanic activity. Did you investigate whether a change in the wind, the major wind directions at the time, like formation of an ice cap could change the circulation in such a way that your sites would get more ash over time?
So yeah, an interesting question, and I'm still working on that. I'm now starting to talk to some people that work in ash modelling, so I can have a better look at that. What I did with the ash is I did a lot of geochemical analysis on the ash, and then I tried to match it to known volcanic sources. And what was interesting is that the only sites that I could really match up well were in southeast Alaska. Very few of the Aleutian Island sites were matching my data nicely. And when I looked at the predominant wind directions, the winds come from the southeast, and today anyway, and blow into the Bering Sea. So I was expecting to find that most of the sources were actually in the sort of central Aleutians, and yet that didn't match my data at all. So it's suggested to me that there was a change in the wind direction at some stage. But the other thing that complicates it is that you might see winds at a low level that are blowing one way, but in the upper atmosphere, the wind directions might be going a different level. And then to further complicate that, the mafic sources probably don't have ash plumes that go as high as the felsic sources. So the felsic sources are much more likely influenced by the high level winds, also than the mafic ones, which would be influenced by the low level winds. So I've got a fair bit more sort of modelling of wind directions. But that's something I'd really like to look at and see whether we can see that there's a change in the wind direction, and whether then that, if why you see this increase in ash at that time.
Do you know, because often in these backup settings, in the deep basin, there's a lot of turbidity players coming from different areas.
Yes.
So I think usually the course from the deep basin and
Yep.
from the soil.
Oh, the deepest part of the basin we got was on the Bowers Ridge.
Yeah.
So whether you get the turbidites there as much, I don't think so.
Because that would be a way to see if nonetheless volcanic activity was taking place. Or if, for example, the central part was not immersed all the time.
Yes.
Maybe we have to vote. I know that's the age of the volcanism of the central age, like the super area one. Maybe it's more recent.
So the age of the subaerial
Yeah, activity in the central part.
is more recent. I think it would have been going over that entire time. I can't see that it would be that, it wouldn't have started just then. The Aleutian was older than that, so
Yeah.
it should have been continuous.
There's been fluctuating in height. For example, the period where most of the volcanoes are submarine, and periods where they become submarine.
Yeah, I'm not sure. I mean, we could easily have a look at that and see what height the volcanoes are to see whether sea level would influence it. They do become more submerged as you go from east to west along the Aleutians. That would just be a deepening of the plate. But I think they're emergent to an extent that wouldn't be influenced simply by sea level change. But yeah, something else to think about. It's quite a complex pattern, and then of course if it's covered by sea ice part of the year, you've got to think whether the volcanic ash fell on the sea ice. And then what we're seeing in the rock record is actually a delay from when it sinks, just to complicate it a bit more.
You mentioned that there is a big difference between before and after 2 years in the microfossils and the main fossils. So do you think what's the kind of reason led to this kind of change?
General cooling of the climate, what we use for glaciation.
Do you think there is something contributed from because it's a margin sea, perhaps we are affected by some input from the continent. Do you think is it possible?
What sort of input?
Like some materials will come from the continent.
I suppose as you get more material from the continent, you may be fertilising the ocean a little more. If you add more sediment, you're likely to be adding, say, more iron into the ocean, which will help fertilise it. You might get more diatoms because of that. But most of what we've seen is that the increase in diatoms relates to high sea level rather than the low sea level when you start to get that flux from the continent. So that doesn't naturally work. But that might be leading to some of the complication in trying to match the oxygen isotope record to the sediment record. Things like that might complicate it. So there's that sort of big change that stands out well, but some of the complexities are not quite well resolved yet.
But if there are no more questions, then let's thank Kelsey again for a great talk.